Well, good morning all, and welcome to another Yara webinar, the series we've been doing over recent years, and delighted to be doing this as a live broadcast, so hoping the technology all holds up for us. There are a few still joining in terms of attendees, but I think in view of the time, and we did say we would start at 11 to respect that, then we'll make a kickoff. So today's webinar then, I guess, is very much about how we can start to improve and build sustainability more into our crop nutrition programs. And when we think about sustainability in crop nutrition, then we've got three aspects that Yara are very much working on and working towards. And that's firstly decarbonisation of existing products, and you would have seen maybe through the media yesterday the first global partnership where green ammonia will feature in growing crops in Sweden. So that's a world first that happened there yesterday, the first step in decarbonising existing manufacturing towards green ammonia. Secondly, then we've got utilising fertiliser better in terms of improving nutrient use efficiency, and continued work there when it comes to digital tools such as @Farm and N-Tester. And you'll see some announcements coming through more on that as well in the coming days. And then finally, we've got sort of development of new products when it comes to sustainability and how we can do better at recycling waste and reusing nutrients. And that's really what the theme of today is about. And Yara took some first steps into this arena by forming a partnership with Veolia, the large global waste business, and that then set up and established the Nutrient Upcycling Alliance, which a number of partners are involved, as we look to really try and improve management of waste and bringing it back through the circular economy onto farm. So today's webinar is very much thinking about that third strand that I've just mentioned there. So I'm delighted to be joined. So myself, it's Mark Tucker, and I'm delighted to be joined by Dr. Ruben Sakrabani, who's the soil chemistry associate professor at Cranfield University, and Yara have recently established a partnership with Cranfield to really work in this area of organo-mineral fertilisers. So the scope of the discussion, and I'll get Ruben to introduce himself in just a moment and take the discussion on, but the scope really of this morning is that we're going to learn a little bit more in terms of really what an organo-mineral fertiliser is and what some of those anticipated benefits might be and how they can feature. And then as we move towards the end of the webinar, then how can you get involved? But do remember, post questions throughout the next half an hour, and then we can address those with the Q&A at the end as well. So yeah, I'm going to ask to now hand over to Ruben Sakrabani. I'll stop sharing my screen and Ruben will then have his screen up and hopefully is there to introduce.
Good morning, everyone. Thank you, Mark, for the kind introduction. I'm Ruben Sakrabani from Cranfield University, and it's a great pleasure to be here to discuss about on the topic of organo-mineral fertilizers. So I'm calling my presentation Challenges and Opportunities for Using OMF in Promoting Sustainable Agriculture. My area of research interest is on soil fertility and use of organic amendments, and organo-mineral fertilizers is one of the products that I've been working on since 2006. I'm trying to move on to my next slide, but yes. So basically, I will provide you an overview of the background, some headline messages, and then I will describe a little bit about what OMF is and some of my own research findings and research findings of others. and then I will conclude it by a SWOT analysis. So in terms of headline messages, as you can see in the slide, nothing that will not be of news to you in terms of the the challenges in terms of mineral fertilizers. As you can see from the graph, that nearly half of the food demand globally is supported by mineral fertilizers, and obviously it plays a key part in agriculture. And at the moment, we are having a lot of challenges in terms of energy prices increase and the consequential impact on fertilizer prices. And also in the background of this, in the global map, you can see in terms of nitrogen, excess nitrogen per hectare, there is actually a lot of excess nitrogen available. So we also need to also not only improve the nitrogen nutrient use efficiency, as Mark mentioned, but also try and find ways to use new products. And I can't not mention about the COP26, which was happened last year, in terms of how whilst greenhouse gas emissions from agriculture plays a key role, it not really get the attention it deserved. So I think a lot has to be done in terms of improving the sustainability and making agricultural production viable going forwards. So about 6% of the global greenhouse gas emissions comes from food losses and waste. So clearly, this is something that we need to minimize. And the initiative as mentioned by Mark Tucker, such as the Nutrient Upcycling Alliance, goes some way to address this and trying to valorize and improve the efficiency of these food losses and then turn it into a resource. And that's something that I will go into details. In a related context as well, soil degradation is prevalent in whichever part of the world, and the definition of soil degradation, as you can see in front of you. So I'm not going to go through that in detail, but nevertheless, it is prevalent. So in the parts of the world where we are, it is still there. So in the context of degrading soils and trying to actually marry that with trying to improve the nutrient use efficiency, farming and agriculture is really challenging in terms of trying to address these together, and also in the context of improving food security. So this is my slide that kind of provides a slightly simplified summary, but puts things in context and hopefully sets a scene for the future, for the next slides to come. So this is two sides of the coin. So if you look at the left-hand side of the coin, you've got population increase and food demand. That is something that we can't stop because it's going to be on the increase. But then the food demand is actually facilitated by the increase in mineral fertilizer use, which is then it's vital for high crop productivity, which has also been seen in the first slide, where nearly 50% of food production is obviously heavily supported by a mineral fertilizer. But what happens on the other side of the coin is it's reflected in the impact of the crop productivity. So as the crop is growing, it's actually drawing the resources from the soil, which is what I indicate as soil organic matter, SOM, which is the biological active part of soil that makes soil a living thing. And this soil organic matter is key because it's a sponge that holds on to nutrient, to moisture. So, it's really key. So the reduction in the soil organic matter, which is related to the soil degradation that I mentioned earlier, make sure that the reduction in the nutrient retention, it also facilitates, it's also enhanced, which means you need more mineral fertilizer. If the soil organic matter level is preserved or conserved better, then we probably, the nutrient retention will be greater, which means we need probably lesser mineral fertilizer, or we can augment it with alternative products such as this organo-mineral fertilizers. And that side of the coin is the bit that I'm trying to work on in my research to see how that can work very closely together with crop production to ensure that, whilst we still have to fulfill the food security agenda, we also do it in a sustainable way to balance with food production and also making soil a healthy system to continue the production going forward. So this is going a little bit more detail into the carbon cycle. So the key message is that it shows the fluxes. The arrows indicate the fluxes and the values are in gigatons of carbon. It shows the fluxes of carbon between the different parts of the ecosystem. So my main focus will be on the terrestrial and the atmosphere. And you can see carbon is also present a lot in the aquatic environment, but that is something that I will not go into detail. So if you just focus on the two numbers, if you look at the 2190 and the 750, that shows there's up to 3 times more carbon stored in the terrestrial ecosystem, and how we actually manage that through all the practices that you're familiar with in agriculture is really vital in terms of its impact and consequences to what gets liberated to the atmosphere. So that's where my research is trying to focus on. So this is going in a little bit more detail into the soil carbon cycle itself. So carbon in the soil below ground, it does not exist in one form. It exists in different pools, as we call it. And what we indicate that is in turnover years. So the turnover year of tens to hundreds to thousands. So ideally, the carbon in the soil should be stable, because as the earlier slide shows, if you've got up to 3 times more carbon in the soil, the more stable the carbon is in the soil, the less it would be liberated back into the environment as CO2 or methane, depending on the situation. Of course, the carbon in the soil cannot be completely stable. So we've got to make sure that the carbon is distributed not equally, but in an appropriate manner in terms of how it is distributed between the what is the quick turnover, which is indicated by a simple molecular structure, as compared to a little bit more stable one, and also very, very stable like charred material. So all of the carbon cannot be in one pool or the other in the extreme. They've got to be in a balanced approach. And the organo-mineral fertilizer and organic sources can play a role in trying to make the carbon stability, and also ensure that carbon is also a vital substrate for soil microbiology, and that also makes a soil a healthier living system, trying to also tackle the degradation challenges and make soil a healthier system for food production. So the next slide shows some data from field study looking at ley, which grass in rotation, and its impact on productivity. So this slide shows a table of different soil textures, clay loam up to silty loam, and shows us the percentage of organic matter at the start of a trial, and following on with ley, and also what happens to that when it's converted back to an arable intensive system. So if you look at just the first example, you've got 3.1% clay, 3.1% organic matter in a clay loam soil. After 3 years of ley, you can see there's a buildup of 0.1%, so it goes to about 3.2%. After a further 9 years, there's a further buildup of 0.5%, so it goes to 3.6% compared to the start. However, after the 12 years of ley grass in rotation, when you convert the land bank back into an arable intensive system, then you can see that the percentage has gone back to 0. What this means is that it's gone back to 3.1%. So the 0.6% organic matter that has been accumulated over 12 years is just zapped out by an intensive system. So the key message here is that the rate of buildup of this organic matter, the biologically active part of the soil that makes soil a living thing, is very, very slow, but the rate of utilization when an arable intensive system is in place is very fast. And this buildup, this very slow buildup and very fast utilization, is obviously very clearly dependent on the soil texture. And that's the key message from this slide. So in the context of that, colleagues at Cranfield University, where we hold the National Soil Inventory, so we are custodians of this National Soil Inventory, which is a soil survey that was done in the 1970s and late in the 1990s, where soils were collected at every 5 kilometer grid square throughout England and Wales, with top soil chemistry analyzed, and one of the parameters analyzed is soil organic carbon. And this shows a spatial distribution throughout England and Wales of the original soil organic carbon content in the 1970s. And then the rate of change shows the change as has happened when the resampling was done in the 1990s. So we've got two actual values of the same land use that was in the original situation, 1970s, and also the 1990s. So it's comparable because it's the same land use. And the key message here from the first map, it shows that the original carbon content is high in the upland soils, and obviously it's lower in the arable intensive part. You can see East Anglia with the arable intensive part, the color coding is much more lighter, indicating the soil organic carbon content is lower, which is not too surprising. You've got some hotspots of high organic carbon contents in southwest, in Wales, and also the upland soils. And the rate of change shows the change comparing the second sampling that was done in the 1990s and the first sampling, and what the change has happened. So the rate of change shows, a very similar pattern. And the key message here is that the higher the organic carbon content of the soil at the starting condition, the greater the rate of loss. And where this loss is going is something that we are not entirely sure whether it's going released all up to the atmosphere or whether it goes as diffuse pollution. We don't have enough evidence of that, but all we know is that it is changing. And if carbon is such a key parameter that's important for soil health, we really need to conserve and find ways to make sure that we optimize the sequestration potential of this process by actually conserving and managing the originally high organic carbon soils that are very, very important. But nevertheless, the organic carbon soils which are lesser in the arable intensive part would also still need attention and will also need some continuous practice and implementation to ensure that the rate of change is slower and not very fast. So coming back to what this organo-mineral fertilizer is basically a definition that is suggested by the European Fertilizer Regulation. Is basically a co-formulation of one or more inorganic fertilizer and one or more organic component to it, which is of biological origin. And I'm not going to go through the parameters there. It just gives you indication of what should be the levels of nutrients and some of the micronutrients and also some potential contaminants that can be allowed, and also how it needs to be controlled, so that we have got some measure of how to actually we know what we're actually adding to the soil when we consider it as part of your fertilization regime. Some of the work that has been done so far, literature search shows, as summarized in the table here, it shows the typical crops that have been utilized, what are the feedstocks that has been used to produce these organo-mineral fertilizers. And I've simplified its impact by showing a upwards down arrow to show a positive response, a downward arrow to show a negative response, and a side-to-side arrow showing no particular significant impact. And that's how I've simplified it. If you look at the response to the crop, predominantly there's an upward trend. In some cases, there's been no significant impact on the crop response. And on the impact of the soil, predominantly there's also a positive response with some indications where it has been negative. So this is again not an exhaustive list. This is just an indication of some of the work. The work on OMF that I've been doing is since 2006. There isn't, and some work is still in progress as well. So this just shows you a brief overview. So what do we know about what is out there in terms of OMF from a scientific perspective? Is what I've shown, but we also do not know a lot about it. For example, we need to know about the impact of the C/N ratio, the impact of the pH, and how that can influence the carbon stability. Because the feedstock for these organo-mineral fertilizers come from organic sources, they can also come with the inherent contaminants and how they would in fact impact the final quality. We need to know of the monitoring. We need to do more monitoring into the impact, because some of these impacts of these organo-mineral fertilizers are not short, they could be long-term. If you want to make it really a truly green fertilizer, we also need to make sure the impact of this OMF on the greenhouse gas pollution emission, and also potential wider environmental impact in terms of diffuse pollution. Because of the biological origin, traceability will be a challenge for these organo-mineral fertilizers. How stable is the carbon that is present? Will it be liberated as CO2? How to actually monitor it? So there are some new tools such as near-infrared and mid-infrared based technologies. Most of the feedstock for producing these materials will be wet, so the drying will be key, and that will have energy implications, and that would be reflected on the final price. What's the physical nature of the OMF? You want it to be an ideal pellet or granule size that you can actually use your conventional spreaders. Will it spread the length of the 24, 36 meters that you would want? Will it shatter? All these things are things that we do not know enough about. There's already some body of knowledge already, such as the information by the organic and organo-mineral fertilizer industry in Europe. There was a conference that was held in 2019. So there's some work that's already being done by colleagues in Europe. Some of the feedstocks, as you can see here, it could be cattle, slurry, poultry, litter, farmyard cattle farmyard manure, pig slurry, etc., digestates and biosolids, and it shows the potential available nitrogens, and the organic and the mineral fertilizer or proportions of it, and how this can be utilized to be some of the component of these organo-mineral fertilizers. Some of the work that I've done is based on sludge-based organo-mineral fertilizers, where we added urea to provide the nitrogen and potash to provide the potassium, and the phosphorus is from the sludge itself. And in this case, we granulated it and we produced an end product which was 90% dry solid. And then we had two formulations, a 10-4-4 and a 15-4-4. And then, we carried out field trials. This just shows a summary of the technology that was used, where you can see the dosing of the nutrients happened to this digested sludge cake, and it went through a granulation process. And then the excess waste heat from this granulation process was recirculated to dry it, and then it was sieved to a particular diameter so that it is all uniform, and that way it will be a product that is easily to be spread. One of the challenges that we did not overcome was the drying technology. Whilst using waste heat, it was not enough to dry completely to get to the 95% dry solid final product. In that sense, we had to actually pump in fossil fuel, and that's where it was not truly a green product as you would like. But that's something that has been overcome in recent years, and some of the other examples I will show will reflect this. This is how the product looked like when we applied it in our field trials. So, and the origin of this material is from biosolids. So we carried out field trials in Cheshire. We had spreading trials. We made sure that it spread to equal distance using conventional spreaders, because we do not want farmers to use new tools. So that all was carried out successfully. We had trials on cereals as well as on grass. This just shows plots of different treatments and how the distribution of the different treatments and the crop responses were different depending on the treatments. This just shows some of a diagram on the field trial that was carried out, and this work has been published. Field trials from over 4 years on major combinable crops. It shows the key message here is the conventional fertilizer, mineral fertilizer, and the organo-mineral fertilizer. There was no significant difference in terms of the crop yield, just showing that we could potentially rely on this new product without impacting on the yield. So again, the two sides of the coin that I showed earlier on in the first slide is the food security agenda that we're trying to address here, whilst improving resource efficiency and still conserving soil health. So in our work, we also found that, considered, in terms of the development, we need to make sure that, it is, the product is granular. We don't want it to shatter when you have the spreading trials, etc. So we don't want to have dust. We want to be chemically, having the right appropriate nutrient ratios to meet the crop demand. We want to be biologically stable. We want to use it for dressing purposes, surface dressing, so we want to make sure that, it is actually easy to handle in the economic practices. So obviously we also want to get it to be marketable. So you want to make it as an end product. So we also need to make sure we've got the scientific evidence to turn it into, an end product by getting this end of waste status. So this is all the things that we provided in terms of evidence. So we also were mindful of the logistical challenges. So, for example, if you are transporting wet material from further afield, that is obviously additional cost, which is why the drying technology is important. We want to make sure that we are applying it at the right conditions. So similar to all the practices that you're actually deploying at the moment when you apply your fertilizers. So we also want to make sure that we are mindful of the environmental impact, and also in the particular case of biosolids, we want to be mindful of any PR issues as well, and also nuisance in the sense of odor. But in the OMF product, because of the granulation of the drying, the odor challenge was significantly overcome as compared to just applying the biosolids on its own as a cake, which is usually the practice. So some of the new work that I'm doing, moving on to another technology based on carbon capture. This is provided by a company called CCM Technologies that I'm working with them. And in this case, the CO2 is captured from a point source. And then it is also mixed in with calcium nitrate and aqueous ammonia to provide the nitrogen supply. And in this case, the organic material is a plant residue and also some livestock manure. And then in the process of mixing it with the ammonium nitrate and aqueous ammonium calcium nitrate, the heat that is being liberated is then recirculated to dry and then is pelletized. So in this product, we have carried out the field trials over 1 season, and we've got further funding to carry it out over another 3 seasons. It was carried out at the Lutonau Estate in Bedfordshire. So the first year trials for winter barley and winter wheat showed that, as you can see, we had 3 formulations, so 5%, 10%, and 15%, which is indicated by F1, F2, and F3. And then CF is the mineral fertilizer, and then the control. So you can see that, and then the 50% is basically 50% of the optimum dose. 100% is the optimum dose that the farmer had used. And then 150% is 150% on top of that, and then 200%, so double the optimum dose. So you can see here that when you compare the F1, F2, and F3, which are all the mineral fertilizers, compare it to the, F1, F2, and F3, which are all the organo-mineral fertilizers, when you compare it to the mineral fertilizer indicated by CF, you can see there's no significant difference for both the winter barley and winter wheat. And the value of 6.35 tons per hectare was in the main farm. That was the yield from the main farm using the conventional mineral fertilizers, and the winter wheat was 8.14 tons per hectare in the main farm. And you can see in the slides, in the graphs, you can see that the values that we got for winter wheat and winter barley were quite comparable to the main farm, which was done in exactly the same soil and crop husbandry. The only difference is that in our plots, which is the data I'm sharing in front of you, was using the carbon capture fertilizer, but in the main farm, they were using the conventional. Again, providing some evidence that, early evidence, but it's just 1 season. So we need to do more work, but early evidence to show that, the yield has not been compromised. This is just some trials that was done in France, just to give you an analogy of what's happening abroad. The figure that you see in front of you on the left-hand side, the value of 1, the y-axis is a ratio. So 1 is the perfect ratio where the amount of yield that is being produced comparable by using a mineral fertilizer, and anything lesser than that is obviously something lower. So it shows, the slide shows the yield response for this ratio for maize and wheat for a range of organic materials, a sludge compost, a bio-based compost, a manure, a household compost, so indicated by these acronyms. So the key message from the first slide, it shows that over successive years, so each bar is each year. So you can see over successive years, you can see that by using repeatedly this organic material, you can see that the yield is creeping towards the ratio of 1, which is the comparable ratio to a mineral fertilizer. So that's what it shows. In some cases, after many, many years, you can see it goes even beyond 1, which is obviously goes slightly even beyond the mineral fertilizer. And the infiltration rate, which is shown by the figure on the right-hand side, shows that when you use these organic mineral materials such as the indicated by the acronyms OMR, BIO, and FUM, compared to the control, which is indicated by the TEM, you can see that in general, the infiltration rate is significantly better, which is due to the organic matter. And that's not too surprising. This just shows some further evidence. And the last figure shows the carbon stock in soil that shows over repeated years. You can see there's a gradual buildup of the carbon using these different materials, but the buildup is actually very, very slow, and it takes many, many years to get this buildup. Again, this comes back to the carbon below ground that I mentioned earlier on in the slide, that shows carbon is prevalent in different pools. You know, the very easily utilized, the kind of the intermediate, and the very, very stable. So is this carbon distribution between these pools is key to show how that buildup can occur over time. If all the carbon is very, very labile or very easily utilized, then the buildup will be very, very slow. And on the reverse, if all the carbon is very stable, the buildup will be very, very fast. So getting the balance right is key. And the last slide is basically showing a SWOT analysis, a strength, weakness, opportunities, and threat of what this organo-mineral fertilizer is about. So in terms of the strength, there's some evidence to show there's increase in organic matter, water holding capacity, the biology. There's also reduction in soil compaction. It's a carbon resource, you know, it's using some residual nitrogen, and also for organizations which are concerned about corporate social responsibility and sustainability. This is really one of the ways forward, as Mark mentioned in his introductory talk. And also it really tackles the climate agenda, where, you know, one of the mitigation steps amongst many others is to look at the potential to sequester carbon in soil, which has got 2 to 3 times more, you know, stock compared to the atmosphere. In terms of opportunities, there's carbon credit, which is still an early story. So we need to gather evidence. There could potentially be remuneration for farmers. We've got lots of new policies that's coming, which you're familiar with. And it obviously tackles all of this. There's lots of innovation at the moment, like the carbon capture technology. There's also plasma technology, which I'm also trying to delve in. You know, we just really need to improve the awareness and the education of this. And also there are new tools such as Internet of Things, artificial intelligence, remote sensing, which can be used to monitor and to see how, you know, buildup of organic matter, carbon can be prevalent. There are obviously challenges, so there's traceability is key. We need to make sure that, you know, how we can ensure that's the case. There are potential contaminants, so the supply and the quality of the feedstock, a wet feedstock, the drying, you know, the energy implications and the cost implications, all that are very key, because that will all be passed on to the customer. And in terms of the competition threats, it can also be, there are other products. You know, this is a new product, so farmers, you know, maybe initially may have lots of questions, which is why we are trying to obviously share some of the knowledge we have. Uncertainty, you know, how much are the farmers willing to pay? They wouldn't want to use new machinery, which is why we try our best to make sure that, you know, it is easily spreadable. You know, certification, you know, end of waste, you know, all these things are potential challenges that we need to overcome. But by providing the right scientific input and know-how and working together with industry, I think this is something that we can easily overcome and take it forward in order to ensure that food production obviously can't be compromised, but nevertheless, at the same time, we also make sure the soil health is preserved, and to make sure that we carry out the entire crop and agronomy production in a sustainable way moving forwards. Thank you.
Great, many thanks, Ruben, for a nice rundown there. I'm just going to change presenters again, so we just get the slide back up.
Okay.
So I'm hoping now that that's...
I can see a slide. If you can make it full screen, maybe.
Yeah, there we go. So yeah, great. Thank you, Rubens, for yeah, really sort of interesting view of where we've got to with regards to organo-mineral fertilizers. We've got some questions that had come in advance, but also there's one showing there. We'll come to those in just a minute, but just to continue on from Ruben's presentation there, then what's new in terms of and why we've sort of sparked this webinar and wanting to take things forward, then as I mentioned in the introduction, then we've started work with the Nutrient Upcycling Alliance, and we've embarked on initial trials with regard to organo-minerals to see how crop performance comes through, and already Rubens has mentioned some there. And what we really want to do is continue the momentum of our activities in this area as we start to sort of build our knowledge and take things forward. So one of the areas we'd like to embark on is starting to get farmers involved in building our understanding and knowledge of this. And as you can see on the screen there, we've got something that was just termed offer by way of an organo-mineral fertiliser farmer experimental research. So really what we're now looking for is farmers who would be really interested in seeing how these products perform. We don't know exactly what volume we'll have over the next few weeks coming through, but we will have a small volume of product which we can start getting on to hopefully a spring cereal crop in 2022, so that we can start to understand more from a farmer point of view and a field performance point of view how these products work. We're thinking that they offer the opportunity to be that initial base dressing by way of putting in some nitrogen, some phosphate, some potash, some sulfur early into the crop nutrition program, and then we would follow that application through with a conventional product. And I mentioned our nitrogen sulfur grade Yara Nature there as part of it. So really what we would are asking for now is for farmers to show their interest, really, to be involved in a study where we gather farm data from sort of start to finish through a season, which will add to our learnings alongside the more technical R&D work that we do with Cranfield. So yeah, I'm going to run a poll in just a second, which hopefully will ask you in terms of whether there's an element of interest there, which we can put, sort of then move on with following today's webinar. So that's going to come up on your screen any minute now, which will just ask then to you to answer that. It's gathering responses at the moment, and it looks very encouraging. Yeah. We've got 60%, over 60% voted so far. We'll just let it run just a moment more. So it looks like we're about there. So yeah, 63% what I'm seeing on my screen showing that are interested. So that's really encouraging. What we'd like you to do really is sort of follow this interest through by getting in touch. There's myself, Mark Tucker, there's Natalie Wood, or your Yara representative, so that we can really gauge a level of interest and then be in touch with you to sort of take it forward. So that's great. Thank you for that and the participation in that. Now let's just move finally for a few minutes on the Q&A side of things. Then there's one come through for definite, which I'll just ask Ruben. Is there any indication of what cultivation was used in the French trial that you highlighted? Is that something you have any sort of knowledge of in terms of whether it is a specific cultivation technique being used there?
I don't have insight because this was something that was not my own work. I can certainly find out and come back, but I don't have insight at the moment. I'm unfortunately sorry.
Yeah, no worries. Well, we can, yeah, Paul on the line, we can.
I can send a response to you, Mark, and if you can forward it to the, yeah,
certainly will.
I can find that, yeah.
Another question really is in a view, Ruben, on terms of the availability of nutrient from this type of product, in terms of when we compare them against classic. You sort of highlighted a bit there in the presentation, but how quickly does the crop respond when we apply a product of this nature?
Yes, that's a very good question. Yes, so for example, we did our controlled trials, also like in laboratory context, we found that up to about 90 days, where the mineralization happens. In our field trials, we found that the response was really good, and we applied in the split application just as what the farmer has done as well. So we follow exactly the same. So in that sense, the availability of the nitrogen in this particular case was quite encouraging.
Yeah. Yes, another question here. How would the product fit when using cattle FYM? Have you got a view on that, Ruben?
What's the question again? Sorry.
How would the product fit when using cattle FYM?
So I suppose in the current OMF that we have used, our residue was crop residue and also poultry litter. So I think for cattle farmyard manure, I think if you're using which I assume you'll have a lot of stubble in it, then it would provide some nice ratio of stable materials. In that sense, it will be good for as a feedstock for absorbing nutrients. So I think it will be a good component in the OMF mix. But I think it all also depends on what other material you're mixing it, because remember the OMF is actually a blend of two or more organic components and mineral fertilizer, you see. But I think the farmyard manure has got a good potential because it's got the straw in it, it's got the manure in it, and that can be a good sponge for holding on to nutrients.
Yeah, and another question in terms of how do they spread? I think I can add as well, but
Yeah.
Ruben, how do they spread when you out in the field and can farmers, another question, use sort of conventional equipment?
Yeah, in the field trials that we carried out for the carbon capture, we only use hand spreading because ours were just plots. But the farmer has been convinced by our work, and he's actually going to apply this on his farm at a farm scale, moving on from our plot scale using conventional spreaders with Amazon, I believe. And in our previous work using the biosolids derived OMF, we also use conventional spinning discs, and we did not have any challenges with the width that the spread happened. It all happened really very uniformly, and it worked basically. Yeah.
Mm. And that really does mirror what we've seen in this. We had some initial spreadability done in France and achieving some very good spread patterns with the product in France, and also where it's been developed in Finland. So yeah, it does seem that conventional equipment, and even in Finland, they've been placing the fertilizer at planting. So seems to be working okay with that conventional equipment.
Yeah.
Yeah, how does a trial of a new product such as this affect your compliance with farm assurance schemes? And I think, yeah, I'll just add a comment. I think at the end of the day, these products are come in and are in an EU fertiliser status position. So as long as they're classified as a fertiliser, then I think they should be not a problem in terms of compliance. But Ruben, do you want to add anything there?
Yeah, that's right. So basically what we're trying to say, we're trying to gather evidence really that, because this is a new product, you've got to gather the evidence. So that's the evidence we're trying to gather to show that actually it's not going to, hinder the process of the farm assurance scheme. So far, it's been good.
Yeah. Another question that was in, have we talk to the maltsters? And just to say that, yeah, one of the trials that we'll be doing, we haven't spoken to them yet directly, but one of the trials we'll certainly be doing this coming year is to work with spring barley in some of the work we're doing with a new partnership with Cranfield. So yeah, the malting sector will be very much included in work as we go forward. Any more questions there just coming through? Yeah, I guess one question, Ruben, in terms of organic matter and what sort of quantity is in these products, and is there any idea of the time frame if you use these products for a number of years, how they would affect that organic matter status and perhaps the profile of the organic matter in the soil?
Yeah, so for example, in the recent one that I shared with you in our trials in Luton Hoo, the inherent, so before the application, the carbon organic matter content was about 3%. So it's not that bad. And we did not see any increase because, as I said, it's only one season, you see. So, and I don't anticipate seeing any increase because as even some of the data that I showed from the work in France, that the buildup is really very slow. And if your soil texture is of clay, then obviously the buildup, will be a bit more faster because of the protective nature of clay. And if it's very sandy, it will be the opposite. So that's the best I can answer for now. I can't really give you a time frame, but there are ways and means to actually find out by using some carbon modeling work, which I have done in the past, but I have not done for this particular product as yet. But
Yeah.
it will not be a quick process, that's for certain.
Mm-hmm. And some of the products that I've seen that we're exploring, they're typically around 35% organic matter. So when you work out alongside the application rate, then it does seem to be putting on quite a decent quantity of organic matter. And that does go to one of the questions that's been posted there, which is, do we know the price of the product yet? And do we know the kilograms per hectare? Pricing is currently being worked through in terms of what these are. So we will have an indication of that in the weeks ahead. So I can't give you an absolute on that, but certainly being worked through. And then kilograms per hectare, then, I think typically we'd be talking, and certainly what I'm thinking at the moment, a product we're looking at would be about 800 kilograms a hectare, that sort of quantity. So I think it is something that we have to be aware of with the OMFs, that to get the benefit of the organic material, it's that balance between an application rate and a nutrient concentration. So yeah, did you have application rates in your experiments there that you could just allude to?
Yeah, so basically, as I said, we followed the in our experiment we had the 50% less, and then we've got the 100%, which is the optimum, which is what the farmer had applied. So I think he applied 250 kilograms of nitrogen per hectare. So we then obviously compared our application to that, you see, in terms of we had to apply quite a lot. And then we also over applied by 150% and then 200% because we wanted to get the yield curve, you see, so which is why we went through this approach. But I think what the farmer in Luton Hoo would do, I don't know the details of that yet, but I know for certain that he's going to go ahead with his own farm scale trial. But in terms of the application rate, I haven't got any insight on that yet.
Yeah, I think when we look, if we
Yeah, sorry, but I think we would probably need to apply quite a lot, as you said, Mark, because to because in our case, if the nitrogen content was 5%, 10%, and 15%, so it's definitely much lower, you see. So to match what the particular target you would need, if you were to apply the conventional, you clearly have to bulk it quite a lot. So round about the figure of 800 seems,
and that's what it's very much that nutrient content, isn't it? So 8-10% nitrogen then to give a base dressing, which is going to supply a reasonable quantity of nitrogen as a starter fertilizer for that barley, and then we come back with the top dressing. So at the moment we envisage about 875 kilograms a hectare, which would be a sort of application at drilling that we apply, and then we follow it with a top dressing to manage the nitrogen according to sort of final crop requirements. Just check on any other questions. Can't see any there, so I'm just going to come back to I guess we've done the timeline. What are the big waste streams when it comes to manufacturing organo-mineral fertilizers, in terms of where are the sort of opportunities for feedstocks for these products? Ruben, comment on that?
Yeah, so I think poultry would be good because it's drier at least. It has got a higher N content, so automatically you've got the boost from the N supply. that would be good. But then the other options are like, digestate, and also biosolids as well could be one of them. Either it's coming from biosolids or from food waste, and also farmyard manure as well. But I think you've got to one of the challenges I foresee is the supply of where it's coming from and the transportation, because the way, obviously, as you know, Mark, we've got a lot of uh, there's some poultry in East Anglia, but then a lot of the cattle and everything, is in the southwest. So I think that transportation and the cost of fuel, and if they're wet material, the drying and all that things would be something we need to consider, because all that will have an effect on the final price. Because at the end, this is a new product, so the farmers need the assurance. So they would want to, they will be willing to buy something only if they're really sure about it, you see, because they're obviously very familiar with the conventional mineral fertilizers. But then the challenge is that price is increasing, and we've got so many challenges, so we've got to get the balance right.
Yeah, yeah. And then, there's one final question has just come in there about spreadability again, just to confirm how far it would spread. Yeah, I mean, I think you were using 24 meters. Certainly,
24, yeah.
Yeah, so 24 meters was used in that initial work, and that's certainly the work we've done in France, where we've looked at spreadability. Then we've actually gone out to 36 meters and achieving coefficient of variations of between around 13%, even up at 36 meters. So, and that's the pelletized product. One of the discussions going forward will be, do we granulate or pelletize? At the moment, the pellets seem to be spreading very well. So certainly 24 meters and even out to a bit further than that, you start to lose some of the coefficient of variation as you get to that 36 meters, but very acceptable so far in terms of what we found. So very encouraging. I think in view of that's all the questions that are there.
Okay.
I'm just going to there is another one just there coming. You envisage production to be centralized or diversified on farms, etc., digesters. And I think, I guess I would anticipate this would be, there'll be an element of bringing feedstock to a central position, but we can also envisage perhaps more modular units heading or having production close to where feedstocks are.
Yeah.
But ultimately decided, I think.
I think you've got to have a multi-pronged approach, really, because I think what we need to minimize is, carting the feedstocks for miles and miles. With the current petrol, diesel prices, it's just going to be a real challenge, because everything will add on to the final, product that the farmer will be spreading. So, I can't say it has to be centralized, or I think it has got to be both, depending on the location, which part of the country we are, I think.
Excellent.
Yeah.
Well, I'm going to, I think we're getting to 11:55. Very, very good webinar. Thank you very much, Rubens, for your contributions there, and we look forward to further work and the research that's going to be done. From Yara's point of view, then, please, from the audience, get in touch with us if you'd like to be involved in this sort of pilot study going forward, so that we can progress that. And just, finally, to thank you as an audience listening in, tuning in, and spending some time on this subject this morning. And just one shout out to my colleague Jessica, who manages the behind the scenes bit of this, which is always nervy in terms of relying on technology. So many thanks to all involved, and we look forward to another webinar in the near future. Thank you and bye.
Thank you very much. Bye-bye.